Okay, let's begin. So, first things first, review for the test one is up. Class website. I don't remember the exact link, but if you just go to jhevon.org/teaching, and then click on your class, Math 11 and Math 11 8-R08. You'll see the review there. There's a section where it's going to be. Follow the instructions in the review. So I posted a review, but I also posted some instructions for how to use the review. So that's important. So our test is next week. Is it Thursday? I want to say Thursday. So R08, October 16th. No, 17th. So yes, it's Thursday. So test one, October 16th. So you'll see what topics is covered by the test, as well as you'll see some practice problems, as well as you'll see a mock exam, and I told you what order to do these things in, blah, blah, blah. Make sure you follow the instructions. As far as that goes, let's just pick up where we left off. I believe the last thing we spoke about was a Venn diagram. So this was just a way to visualize sets. And their relation to each other. Now, invented by a guy named Venn. I forgot his first name, probably John Venn or something. I don't remember. But the guy whose last name is Venn, that's why it's always uppercase V, made the Venn diagram. Now what these guys look like is they look like a box. And the sets appear inside the box as like ovals, so I can talk about set A and B. And then the box itself represents the universal set. Right, so that pretty much for the context of this problem would represent everything in existence, whereas particular sets are circles. Use the universal set. So that's the box. Now, one thing that you might want to know is very often Venn diagrams are made in terms of cardinality. Now remember I told you what cardinality was. That was just the size of the set. Or if your set is finite, it is just going to be the number of things in the set. So, for example, I can say something like U be the set A, B, C, D, E, F. Let A be the set B, E, F. Then, if you were to draw a Venn diagram that kind of represents this, you will tend to put the cardinality of things in here. So you might talk about the universe. Now the universe is known to represent the first 6 letters of the alphabet, and you would have a set A in here, oftentimes what you'll see us do is we'll actually write the number 3 here, not because 3 is in the set, but 3 is the size of the set. Right? So this is, that's the size of A. And then we'd write the number out here would be also 3 now, because this box represents everything in the universe, so this is saying I have 3 things here and I have 3 things here, so in total I have 6 things, and 3 of them happen to be in the group, or the set A. And so, let's put another one here, because I don't want us to mix up the numbers here. Now, what is this region around here called? All the region except A. We looked at that last time. The elements that are not in are said to belong to a certain set.
To the complement.
To the complement. To belong to a complement, spelled with an E, which Christine was aware of, but he let me write it down. I didn't know. It's a joke. Yeah, so last time this AC represents a complement, spelled with an E. It's called the complement of the set A. And basically it's everything that's not in A but is in our universe. So a lot of times we'll draw a Venn diagram to talk about the number of things that are in particular regions. And the region of space is in a Venn diagram can tell you what set they belong to. Anything that's outside the circle A is said to belong to the complement of A. Anything that's inside the circle A is said to belong to A. So there are 3 things here in A and there are 4 things outside of A, making 7 things in the universe in total. Now I want to talk about operations on sets. So we can do a kind of mathematics with sets that don't always behave like regular numbers do. So let's talk about that definition. Suppose A be a sets. We can talk about something called their union. Is defined by the following. That's the notation. So it's A union B is how we read this. You can also usually read it as A or B. And it is defined as the inclusive OR. So this itself is going to be a set. It is going to be the set of all x such that x is in A, or x is in B, or both. It's the inclusive OR. Sometimes they put a dot over this to represent the exclusive OR, so it doesn't do the or both part, but we are only worried about the inclusive OR. So it's a set of all things that are in either A or B or both. And of course you should notice sets do not repeat themselves. So if something is in both, it's not going to list it twice, it'll only list it once, because sets don't do repeats. Another thing, we can define A, B are sets. Their intersection is given by, so now this is the notation, A and B. So that's sometimes might refer to this as A intersect B. Or we might refer to A and B. And as the name suggests, that is a set of all things that are in A and at the same time they are in B. In other words, anything that belongs to both sets at the same time is said to belong to their intersection. Anything that belongs to either or is said to belong to their union. So we can kind of combine sets using a union, and we can distinguish who is in both sets at the same time with an intersection. Another important operation is called set minus AB sets. We define A minus B. When I put one set minus another, what does that actually mean? Well, it is the set of all elements X such that X is in A but X is not in B. You can also look at it as pretty much, it's going to be equal to the set of A intersect B complement. That's one way you can look at it. Combine the things that are in A but are not in B. Pretty much how you can think of this, start out with a set A and then throw away all the elements in A that are also in the set B. You'll create another set that we call this guy. So sometimes you might read that as A minus B. A more archaic notation, which not many people use it, but you might see it. So just in case is A backwards slash B. It means the same thing as this. But all the cool kids use this these days. It's more kit notation. Okay, let's make sure we understand these notations before we move on. I think with some examples. Make sure we get what's going on. Where do I want to put these examples? Oh, I'm probably going to need a lot of space anyway, so I'm going to erase them. So, copy these down, I'll erase them and we move on. So, suppose our universe is set of all natural numbers. Suppose A is the set 1, 2, 3. Suppose B is the set 3, 4. Suppose E is the set of positive even numbers. Suppose O is the set of positive odd numbers. Then I wanted to find the following sets. A intersect B. A intersect C. A intersect E. A union O. E union O. A minus B, C minus A, E minus A. Huh?
Where's that?
What's C?
Oh, I didn't write C. C is 4, 5. That example, make sure you can actually complete these sets, know what they are. So example 1, 2. Let's look at a finite universe. set of all integers from 1 to 10, let A equals find A intersect B. A union B. A minus B. A complement. B complement. And the complement A or B complement. We're going to close. Let A intersect B. So in example 1, what is the intersection of A and B? Come again? It's not 3. Not technically speaking. Forget it. Yeah.
Set of 3.
The set contains 3, which is different from set. So remember, these guys are sets themselves. That's it. So all you do is you look who is in A and B at the same time. Not 1 because it's not in B. Not 2 because it's not in B. 3 is also in B. 4 is only in B but not in A. 3 is the only guy that shows up in both at the same time. That is the intersection. Yeah.
Do you include the empty set?
Include the empty set for what?
Like, do you have to say the empty set?
No, because it's not empty. There's 3. Yeah. Yeah, so what is the set of all things that are in both sets? Well, 3. There's a set of one thing that is in both sets. What about A intersects C? Huh? A and C?
Oh.
What's in A and C at the same time?
No.
Nothing. So this is an empty set. That's one way in which the empty set can show up. There's nothing that's in both at the same time. So I open a set, but I can't put anything in it. So that set needs to remain empty. C. A intersect E. Yeah.
Set contains 2.
So E is a set of all positive even numbers. Remember, that's 2, 4, 6, 8, 10, going on forever. 1 and 3 are not even, so 2 is the intersection here? D. What's A union O? Yeah?
X such that X is an element of O, or X is equal to 1, or X is equal to 3.
Okay, so how can you write that down?
X, then the line thing.
Give me a list.
X is an, 1, 2, wait, yeah, 1, 2, 3, 4. But then there's,
It'll be 1, 2, 3, 5, 7, 8, 9.
yeah.
Right, and then now it continues to repeat all odd. Yeah, you could write it out as X such that X is in A or X is in O, but I want you to visually know who's actually contained here. So it's like the set of odd numbers, but you throw in an extra guy. The 2 is like, one of these things aren't like Eulers. E union O. What is E union O?
Something.
Yeah, Lilia? It's actually all natural numbers. Now this is a particular example here of a certain thing, which we'll probably talk about if you don't get it from this. This illustrates an important fact. If you take a set and take the union of the set's complement, you always get the universe. That's always true. For any set A in the universe, that is going to be true. Take that set and everyone not in that set, and you will actually get everybody for any set A. So that's a nice thing. If we group the odds and the evens together, we actually get everything. F. What is A minus B? So pretty much I am going to start with the set A, which was the set 1, 2, 3. And what I'm going to do is I'm going to throw away anyone who's in the intersection, anyone who's also in B. So I'm going to throw this guy away. And so that's going to just be the set containing 1 and 2. G. C minus A. What is that? Set of 4 or 5. In fact, that's just C itself. Which is another general fact, I guess. If you're taking a set and you're subtracting someone that has no intersection with that set, you just get the set itself. So I take N minus E, what do I get? You get O, not the set containing O. O is already a set. E, F, G, H, I. E minus N. Yeah, empty set. You take the set of all even integers and you throw away everyone who's a natural number, well, you're throwing away everybody. Great. So make sure we know what these symbols mean. that's going to be important later. 2A. So this was the shorter one. We should just write this again. 1, 2, 3, all the way to 10. A is 10. The intersection of A and B. So we're going to open the set, write what's in both at the same time. What is that? Nobody. Perfect. So that's the interset. B. A union B.
The universe is
It's the universe. If I collect everyone that's in here or here, I actually create everybody. I have the set of everybody. Now, what about A minus B? It's just A, because there's no one in common. B, A complement. It's actually going to be B. E. What's B complement? It's going to be A. F. What is A intersect B complement? Right, so you look for the people that are in the intersection, which is nothing, and then you find the complement of that. What is the thing outside of nothing? Well, everything is outside of nothing. That is actually the universe here. Now, this is something, we'll talk about this later. But I want you to notice that this is actually A complement union B complement. And that's not a fluke, that's actually always going to be true for something like that. Some of you might even know where that's from. I'll ask you when we actually get to it. G. A union B complement. That's going to be the interset. And by the way, this is A complement intersect B complement. That's always going to be true. Okay. Now I want you to be able to visualize different kinds of set operations with Venn diagrams. Well, since you kind of know how to operate on sets, looking at a Venn diagram, you should know how to recognize what region of that Venn diagram relates to which set. This will help us with solving all sorts of problems. So let's say I wanted to represent just a single set A versus, so there's like a set A in here. What if I wanted to represent A union B? So I have two sets here. What if I wanted to represent A and B? Two sets here. What if I wanted to represent a complement? So one set A here. And what if I wanted to represent A union B complement? And what if I wanted to represent A complement intersected with B? So what I want to do is I want to actually shade the region where that represents the thing that's labeled here. So if I were to shade which part of the Venn diagram represents A, well, that one's kind of easy. That's just shading the circle. So if you're looking at a Venn diagram, you want to pinpoint who's in A, or you just circle all the people in A. What about A or B? What do we shade here?
Both circles.
Both circles. We need to be in A, or we can be in B, or what can be in both. But of course here, these guys are double shaded. You would actually only list them once, and so we take all the shaded regions, entire shaded region. I want to mention here that I drew the circles overlapping. You might wonder, do they always have to overlap? They don't always have to overlap, but if you make them separate, this guy is actually less general. Right? This means you already know that there's no intersection. So if you know for sure that A never intersects with B, you can draw them as separate circles, in which case the union would be shaded like this. However, if you believe they might have an intersection, you're not sure, draw the circles overlapping, just in case. If it turns out that they have no intersection, all you just do is make sure that the cardinality here is given a value 0, like there's no one in here. But if you're not sure, drawing them overlapping, as many overlaps as possible, is the most general case you can actually do. Once you start separating things, now you're claiming to have knowledge of what's actually going on. So don't do that unless you know what you're doing. The intersection. Who's in A and B at the same time? Well, it can be here because that's not in B. It can be here because that's not in A. It can be here because it's not in either. There has to be this region in the actual overlap. So what you want for the one way you can do that is figure out, just shade all of A, because that's this guy. Then you can shade all of B, that's that guy, and then you look for the overlap. So the actual answer is what's in here? What's the answer? So you're looking for intersection, you're looking for overlaps, you're looking for a place where all the shaded regions intersect. A complement, where is that? The box that's not in the circle, so it's everything out here. Okay, let's move here. What is A union B complement?
Everything outside the circles.
So yeah, so A union B was this, both circles shaded. The complement is simply everything outside of that. If I wanted to look at A complement intersect B complement, what I would do is I would first figure out what is A complement, and based on that idea, it's everything outside of the circle A. And then if I found B complement, which is everything outside of the circle B, and now, because I'm looking for the intersection, I want to find the overlap. So notice that I'm doing the intersection. This means I'm looking for the overlap. means what that actually is the places that were double shaded. The place that was only shaded once is not going to work because that doesn't work in the overlap. So this ends up being everything outside the circle, which you might notice same picture. Now, pictures aren't proofs. You can't actually prove that two sets are equal by drawing their Venn diagrams, but they can be quite suggestive and can illustrate how to solve a problem that you're thinking about. So it turns out that these two are actually the same. You can prove them. I'm not going to do it, but the pictures speaks volumes. You can also look at the other one I mentioned. So if I look at the intersection complement, and we look at A complement union B complement, draw the most general picture you can, which means you want to overlap the circles. Then I know that A intersect B is this part, and the complement means take everyone except that part. That's A intersect B complement. If I look for here, look at A complement. Well, everything outside the circle A. And if I look at B complement, which is everything outside the circle B, then the union doesn't require an overlap every shaded region. Anything that's shaded is going to be in the union, and what you would notice is that's actually going to give us everything except, this is the only unshaded region. So it will give us everything except that region, and you'll notice it's the same picture. Last two illustrate a true fact. It turns out that actually, pretty much in general, the complement of an intersection is actually the union of the complements. And the union of an intersection, the complement of a union, is actually the intersection of the complements. You can just complement each set and turn it around. And by the way, this works for more than two sets. So if I had an intersection C, big C, then it would be A complement, union B complement, union C complement, and so on and so forth. And these guys are two very important equations. They have a name. Do you remember what this is called? Anyone do set theory in high school? Anything about sets in high school? It's called the Morgan's test. Many important laws in set theory, but that's a very important one. It tells you how you can distribute complements over unions and intersections. And it generalizes very naturally. Like you can just extend this idea to more and more sets. Let's see, what else do we have to do here? So we have one more problem type to cover for the test next week. And that is solving Venn diagrams, solving problems using Venn diagrams. And so now, I'd like you to turn your attention to the handout that I gave you on Venn diagrams. I gave you last time. We're going to go through those problems. Solve those problems. We're going to use Venn diagrams to help us solve those problems. Let's look at problem 1. We shall do this together. Okay. So, suppose there are 100 students in a school, right? 50 students remember all the math they've ever done. Very good students. Another 40 of students, also 40 of the students are in Math 1108. Of the Math 1108 students, 20 of them remember all the math they've ever done. A, how many students who don't remember are not Math 1108 students? How many Math 1108 students don't remember? Now, this one is not so bad. Because it's a small Venn diagram, which is why I'm going to help you do it, and I'll leave the harder ones to you. So, first thing you want to do in something like this, and this is a very common type of problem. You'll notice that they'll tell you how many people are in this group, how many people are over here, how many people are here and there, or here or there, and blah blah blah. They'll kind of just make that kind of description to you, and you know, kind of it's a Venn diagram problem. It's going to be a problem you want to solve with Venn diagrams. So the first thing you want to do with these guys is step 1, define your sets. So you're told about the number of people who belong to certain groups, and then you're asked about the number of people belonging to other groups. It's kind of a set theory problem. And the first thing you want to do is define your sets. So let's define the other sets. Now there are 2 important things that are mentioned here. We know that the Math 1108 students were mentioned by name, and we have students who remember all the math they've ever done were also remembered by name. So I'm going to define those 2 to be sets. So I'm going to say let M be the set of Math 1108 students. And let R be set of students who remember all their math. That's it. We're going to define names for them. 2, you're going to draw a Venn diagram. So, what we're going to do is we are going to, again, remember the most general Venn diagram will have overlapping circles. So let this be the M set, let that be the R set. Some tips. So you make sure that your circles are all overlapping to make sure you're covering the most general case. Once you separate them, you've made it less general because now you're saying for sure there's no one who's in Math 1108 and at the same time remember all their math. You don't want to be able to say that there is perhaps someone who has both of these qualities. Another tip, fill in the regions with the most overlap first. When possible. Filling in the region in any set. Can also be useful. So remember, we are going to use the cardinalities of the sets here. We're going to actually fill in numbers to represent how many people is in a particular group. So we go back to the problem, we'll read the problem. So I know the universal set has 100 people in it. 50 students remember all the math they've ever done. Also 40 of these students are in Math 1108. Of the Math 1108, 20 of them remember all the math they've ever done. Okay, so what do we want to target here? What do I know about the overlap?
It's 20.
Okay, in Math 1108, 20 of them remember all the math they've ever done. So that's in Math 1108, and you remember 20 such. There are 20 such people in this school. What else do we now know? So that's the region of the most overlap. Now I don't know who is not in any set at all. So what I do, I'm going to fill in the places with the next highest level of overlap. So what do I know about the Math 1108 people? How many are there total?
40.
There are 40 Math 1108 people total. So if there are 20 of them over here, it means I should know how many are over here. That's going to be, it's going to be another 20. Because what I'm going to do is I'm going to take the 40 minus the 20, this 20 specifically, that's going to give me 20 left over. So of the 40 people in the M circle, 20 of them are also in the R circle, 20 of them are outside the R circle. Now what do I know about the R circle? Well, there are 50 students who remember all the math they've ever done. So if 20 of them are in this part of the circle, then there must be 50 minus 20 in the other part of the circle. This is going to be 30 people. So there are 30 people in that region of space. Now, I know that the entire universe has 100 things. So what's left outside of both circles? Well, it's going to be 100, subtracting the 20, and the 30. So what's that left with? Huh? So there are now 30 people outside. And so this Venn diagram is completely filled out because all the regions of space are numbered with a cardinality of the number of people. So once we do that, step 3, answer the questions. So you need a little bit of arithmetic here, but once you fill in from the most regions of overlap out, you can just keep subtracting to fill your way out. Answer the questions. So, in this particular case, we wanted to know A, how many students who don't remember are not Math 1108 students? Yeah? 30. And B, how many Math 1108 students don't remember? 20. which 20 am I talking about specifically? So this 30 here is this 30 here. There are a bunch of 30s and 20s. And this 20 here is this 20 here. Right, so don't remember means you're in the complement of the remember circle. And not being in math 1108 means you're in the complement of the M circle. So our two answers are there. Okay, so now what I want to do is I want to give you guys, let's say 10 minutes to finish the rest of them. Go, quickly. Okay, let's go. Let's see what we've got. By the way, I just pushed all the web work homework assignments that were due before the test. I pushed them to after the test. So your next, so after the 17th. Sorry, really. So the earliest, I pushed all the homeworks to be due the earliest, the 19th at midnight. So you'll have 2 days after the test. I'd rather you focus on going through the review as instructed than worrying about the homework. I sent an email about it, so we'll do that. Let's move on to okay, so we have another college with 100 students. It has 3 majors in this college. It's a very focused college, math, English, and physics. Students are allowed to have multiple majors. So it gave you the list of how many is majoring in math, English, physics, how many are majoring in math and physics, math and English, how many have all 3 majors, and how many major in physics only. And then it asks you how many students are in some of the other groups. So again, first thing we would do is what? Well, call our set something. M is the set of math students. E, set of English majors. Let P be the set of physics majors. Okay, so we're going to draw a Venn diagram to kind of figure things out here. What does your Venn diagram look like? 3 overlapping circles, right? Because they can have multiple majors with what the problem said, so we want the most general situation where we must have a region where all 3 overlap and any 2 overlap, so that's the right way to do it. Math, physics, English. Okay. So now we start to fill it out. And again, filling it out from the region of most overlap is probably where you want to go first. Only is also on the higher only also suggests regions, forgot to mention that over there, that can be filled out early. So some regions you can't really fill them out before you have information from other regions because you have to subtract it. But when it says only, you kind of know, okay, there are only this in that region, you can do that. So, what's the first number we fill in here? 14. Where does 14?
Oh, look at the next one.
5.
5, right. So 5 students have all 3. So I know the region of all 3 overlaps. That's pretty good right there. I also know that 20 people have physics only. So that means there are 20 people over here who are not doing anything but physics. Okay, so now let's talk about, who else did you fill in next? Okay, math and physics. So we went from the region of 3 overlaps, now we want to do the regions of 2 overlaps. You always do the most overlaps first. So let's do math and physics. So math and physics, we have 10 people, right? So there are 10 people in this group, but we've already accounted for 5 of them, so I subtract that 5, and so I have 5 left. there are 10 people in the intersection of the math circle and the physics circle, where 5 also intersect with the E circle. Okay, math and English would be the next one. We know that 20 people are in math and English. So in this overlapping of math and English, there are 20 people. We've already accounted for 5 of them, so there are 15 left. We have, do we have physics and English? Nope, we don't have physics and English. What else can we do? We already did math and English. Math. Notice that in the math circle, we have all spaces filled in except this space. So we know how many total major in math? Well, 30 total major in math. So this is going to be 30 subtracting all the other parts. So we've already counted for 5 over here, 5 over here, and 15 over here. So how many are left now? 5. What else do we know?
Physics.
Just physics and English.
Come again?
Like the just physics and English. You know there's a little bit of physics. And then you subtract 30.
The overlap of physics and English.
Yeah.
Okay.
Like just physics and English, not. So that would be.
Well, yes, so now physics. Just physics and English, because we know all the physics people. So the only thing missing from that circle is this region. Physics is 50. So in here, we are going to do 50 minus the 20, minus the 5, minus the other 5. And so that's going to be 20 people over here. And then we know English. We have 40 people total in English. So it's going to be 40 minus the 15, minus the 5, minus the 20. How many do we have left?
0.
Huh?
0.
0. So there's no one who's majoring in only English. What job are they going to go? I'm kidding. Just happens to be. This just happens to be the problem. It is not a comment on English majors. Okay, so do we have everything? If we add up all the people, right? Now I'll start with physics. There are 50 people here. Then there are 15 here and 5 here. So that's what? 70 total people in all the circles, right? But is that everybody? Well, no, because we have 100 students in the school in general. So minus the 70. So there are 30 people who have not declared any majors yet. And so now we can quickly answer the questions. A, how many students have no major? 30. B, how many students major in math only? C, how many students major in math and physics only? D, major in English only? Nobody. Okay. So, we do the others and we will pick up with those. So based on the length of the test, you'll have maybe 6 minutes per problem. So if you got through that one in less than 6 minutes, it should be fine. What you can do is try to get faster on some of them, so that if you, for example, have problems with matrices, you can spend more time there. That being said, I will see you guys on Monday. So start going through the review, and the homework is due after, so don't worry about it right now.